Hello everyone, this is Songfan from UESTC. I'm pleased to have this opportunity to share with you our recent work, Passive DSSS. IoT applications are looking for ultra-low power communication. Recently, backscatter systems show us the potential of ubiquitous connectivity with range above 100 meters. Backscatter can also enable the seamless communication to transmit streaming data with very low energy budget. We can also find a number of research papers to demonstrate this progress. However, when we attempt to make backscatter practical for IoT applications, we meet a problem. The problem is the downlink and uplink of backscatter systems are highly asymmetric. Let's first say the uplink. As we know, the receiver of the uplink is a gateway. The gateway can be designed sophisticated to receive noisy signal and do interference cancellation. So we can say even the signal traveled twice the distance, we can still achieve long-range backscatter above 100 meters. On the other hand, the receiver of the downlink is the IoT backscatter devices. Those devices are energy constrained and use envelope detectors to receive the downlink transmission, which is prone to interference and noise. So we have a very short range downlink. Let's compare the downlink and uplink. The effective lateral range must have both downlink and uplink. Out of this range, those devices will become uncontrollable. So the downlink become a major limit to the effective range of backscatter systems. Nevertheless, backscatter systems actually lead the downlink transmissions. We have a lot of examples. For example, when the uplink collision happens, the gateway may transmit downlink control to resolve the collision. In addition, the downlink control can also be used to control the data rate, send the ACK, and control the sensors, and so on. So the downlink is important to backscatter system. The next question is, how can we improve the downlink communication? Essentially, we need to improve the SINR of the downlink. The SINR is a signal to interference and noise ratio. We have two basic ways. First is to increase the signal power. Second, we can suppress interference and noise. For the first way, however, the gateway has very limited transmission power. Maybe we can combine multiple gateways with distributed MIMO to increase the downlink range. But this will increase the complexity of the deployment. In this paper, we show the other way to use spread spectrum techniques to suppress interference and noise. However, none of existing techniques can directly work for the downlink due to the high power consumption. In this paper, we propose passive DSSS. This is the first DSSS scheme for the downlink of the backscatter system. We will introduce the design of passive DSSS modulation at the gateway side. And then we will introduce the design of passive DSSS receiver. Our experiment evaluation show the passive DSSS can improve the downlink SINR by 60.5 dB, which can be translated to 3 times of longer downlink range compared to the conventional receivers. Before we introduce the design of passive DSSS, let's first see how DSSS works and what's the key challenge to achieve DSSS on the downlink. At the transmitter, the DSSS modulation will spread the baseband spectrum into a larger bandwidth by using the spreading code. The spreading code is a pseudo-random signal whose data rate is much higher than the baseband. And then we transmit the digital signal into the air. In the wireless channel, we have interference. The receiver will receive both digital signal and the interference. The digital demodulation will spread the interference and recover the baseband. To recover the baseband, the receiver needs the synchronization between the received digital signal and the local generated spreading code. When they are synchronized, this portion equal to 1 and the baseband can be recovered. However, the synchronization is power-starving. We need to first check the phase of digital signal and then generate the spreading code correspondingly. The whole process needs digital signal process, which is infeasible on backscatter devices. The basic idea of passive DSSS is to shift generation and the synchronization of the spreading code from the receiver to the gateway side. This is our architecture. Passive DSSS use two channels. The first channel, we transmit the baseband after the DSSS modulation. The sixth channel, we transmit the spreading code reference. Both two channels are synchronized at the gateway side, so the receiver do not need synchronization and can directly combine the two channels to demodulate the DSSS. To achieve the passive DSSS, we need to address three challenges. Let's first see the challenge 1. Backscatter devices cannot demodulate existing DSSS signal, because conventional DSSS use phase modulation, but backscatter devices can only obtain amplitude information use envelope detectors. Our solution is to use the envelope to convey the DSSS signal. So the receiver can use envelope detectors to receive the spreading codes. And then we use the difference between the two spreading codes to convey the baseband information using the XOR operations. So the receiver can only use envelope detectors and the XOR gates to demodulate the DSSS signal. The second challenge, passive DSSS use two channels. Each channel may suffer from different interference signal. We use I1 and I2 to represent the interference signal from each channel. So the demodulation can be written as this formula. The problem is this formula includes the interference composition that cannot be suppressed by the spreading code. We address this challenge from our observation. The interference across two individual channels has no correlation. To verify this, we conduct experiments to record the interference signal from the two individual channels. And then we compute the correlation from the two channels. And this figure shows the result. And we can see the correlation is pretty low. So our solution can cancel the interference by calculating the correlation. However, to calculate the correlation, we need to do the signal processing, which has high power consumption. This is the third challenge. And we can see this figure. This figure shows the received signal envelope under interference, which is fully analog. The conventional method is to use high precision ADC to sample the analog signal, and then perform digital correlation computing. The whole process consumes a lot of power. Our solution is to use 1-bit ADC, and then we will introduce our design of analog correlation computing circuits to achieve no power consumption. This is our receiver design of passive DSSS. We use envelope detector to remove the carrier. And then we have the 1-bit ATC to digitize the signal. The XOR gate will combine the two channels together to achieve the digit-based demodulation. Then we try to cancel the interference. To achieve this, we need two operations. The first is to multiply the two interference signal. Actually, this is done by the demodulation. So we can just design the interference cancellation circuit to compute the integration in analog domain. So for more information, please see our paper. To evaluate our prototype, so this is our experiment setup. We use USRP as our gateway, and the passive digital-based prototype will receive the downlink transmission and send the received data to MCU. Finally, the laptop will receive the downlink data and compute the BER. We evaluate the communication performance. Let's first see the performance of conventional receivers that use envelope detectors. As our prototype also uses envelope detectors, we choose one channel of our prototype as a conventional receiver. Then we use both channels. On the other channel, we transmit the constant CW so that we can use the whole circuit. We can see the results is close to the one-channel case. And then we show the communication performance of the passive digital base with 0 dB processing gain. The 0 dB means the data rate of the spreading code is equal to the baseband. And we can see in this case, when SINR is low, the performance improves a little bit. However, when the SINR is high, we can see the performance is even worse than the conventional receivers. This is because the synchronization mismatch between the two channels. The mismatch comes from the slight propagation delay between the two channels. And then we increase the processing gain to 10 dB, and we can see the communication performance is improved significantly. And we proceed to increase the gain to 20 dB, and this is result. So we can see passive digital base can efficiently increase the downlink communication performance. In the next experiment, we choose the conventional receiver with two channels as a baseline, because this case has a better performance of these three cases. And then we choose the passive digital base with 20 dB gain for next evaluations. We then evaluate the interference resistance. In the experiment, we use the real RFID and LoRa signal to interfere the transmission of passive digital base at several distances. We measure the downlink throughput when the interference exists. From the results, we can see the passive digital base can effectively suppress interference of both RFID and LoRa. We also observe that passive digital base has higher resistance against RFID interference than LoRa. This is because digital base has a better performance over the narrowband interference signal. Finally, we show the evaluation of our downlink range. This is a picture of our experiment. We can see our downlink range can achieve the maximum 52 meters. And we also define the communication qualities according to the BER. We can say at the excellent quality, the passive digital base can achieve 3 times of the distance longer than the baseline. Thank you for watching. This is for my presentation. If you have any question, please feel free to contact me.